The James Webb Space Telescope's contributions to science. The James Webb Space Telescope is the most scientifically advanced space telescope created to aid in studying the early universe. Amateur astronomers would have been around as early as the Paleolithic age, with nothing more than their eyes to observe and learn about the stars. Stone Age Astronomy and Astronomical Sites, 2017. Modern advancements in astronomy and space science have allowed astronomers to study deep sky objects with growing ease. One of the most notable advancements would be the James Webb Space Telescope. This space-based telescope is named after James E. Webb, the second administrator of NASA, and is the successor to the Hubble Space Telescope, with notable improvements to aid observations. The James Webb Space Telescope's improvements will allow astronomers to learn about the universe's past and answer questions in the scientific community, such as the very birth of the universe and what may lie in the future. James Webb Space Telescope specifications. The James Webb Space Telescope, JWST, has a complex 5-layered sun shield that acts as a radiator to let the telescope undergo passive cooling. This sun shield is nearly the size of a tennis court, reaching 46.5 feet in width and 69.5 feet in length. Engineers have had to account for the effects of solar radiation by implementing a multi-layer design to combat the telescope's heating, as this could damage sensitive components. This critical feature of the sun shield means the sun shield must always face towards the sun. The heat received by the sun-facing side of the sun shields is heated to 185 Bro, while the optimal operating temperature of the telescope's components is −388 Tuckers, as seen in Figure 1. The JWST will not have the shade of the Earth to protect it, as it has settled in a deep space orbit known as the Sun-Earth Lagrange point L2. This Lagrange point is an ideal position for the JWST, as it will be orbiting the Sun and require fewer corrections by the onboard reaction wheels and thrusters. This Lagrange point saves on the limited fuel and power, as the JWST only has a mission life expectancy of 5 to 10 years. Northrop Grumman, ND. Equipped with a science module known as the Integrated Science Instrument Module, ISM, the JWST can look into deep space at wavelengths that previous space telescopes could not. The ISM contains multiple mission-essential pieces of technology that aid the telescope in achieving images with outstanding quality. The ISM includes the following: near-infrared camera, near-infrared spectrograph, tunable filter imager, mid-infrared instrument with a cryocooler, fine guidance sensor. The ISM and its scientific components work alongside the JWST's 6.5-meter diameter primary mirror, carefully constructed of 18 smaller hexagonal mirror segments. The primary mirror is the largest space-based telescope mirror in service due to the difficulties of getting the JWST into orbit. The primary mirror's size allows the telescope to have a significantly larger field of view than the NICMOS camera on Hubble, covering more than 15 times the area and significantly better spatial resolution than is available with the Infrared Spitzer Space Telescope, NASA and Goddard Space Flight Center, NDA. The conjunction of the ISM and the large primary mirror allows the JWST to observe its targets in both the visible light and the infrared portion of the electromagnetic spectrum. The overall wavelength coverage of the instruments on board the JWST ranges from 0.6 to 28 micrometers. At the same time, the Hubble Space Telescope, HST, has a wavelength coverage of 0.8 to 2.5 microns, as seen in Figure 2. Scientific contributions. The JWST's predecessor is the Hubble Space Telescope, which has been in operation since its launch in 1990. With the advancement of technology in the last 30 years, the JWST improves on the HST's abilities and works in conjunction with it to further expand astronomy's understanding of the universe's beginnings. The JWST differs from the HST in that the JWST's orbit is at Sun-Earth Lagrange point L2, while the HST sits in orbit 570 kilometers around Earth. The HST provided decades of essential data regarding the universe's age and how galaxies might have formed. Due to the technological restraints of the time of HST's commencement, the HST can only see as far back as approximately 1 billion years after the universe's birth. The JWST looks to aggrandize the HST's achievements by being capable of observing the very inception of stars and galaxies, approximately 400 million years after the Big Bang. Though the question of when the universe's first sources of light would have formed remains, one of the JWST's missions is to discover the answer to this question, and many more. NASA and Goddard Space Flight Center, NDB. The JWST has provided valuable data pertaining to its initial expectations and goals given by NASA. The previous limit of astronomy's scientific capabilities with the HST restricted the ability to see earlier than 1 billion years after the Big Bang, as seen in Figure 3. These restrictions forced astronomers and astrophysicists to theorize about the formation of galaxies and cosmic reionization. The scientific community will utilize advanced capabilities of the JWST over the next 5 to 10 years to observe how the universe transitioned from its dark ages into the first source of light with the influence of cosmic reionization. This reionization began after the Big Bang, when the universe was rapidly expanding while also cooling to a point where stray electrons could bond into hydrogen atoms. These particles of hydrogen in the intergalactic medium shifted from a neutral to an ionized state and initiated the accumulation of galaxies. Robertson, 2022. The JWST will seek to answer what may have been the source of the ionization, the formation of the first galaxies, the birth of stars, and when the first light occurred. Summary. Astronomy is at the forefront of what could be the next paradigm shift, thanks to the technologically and scientifically advanced JWST. This New Age space-based telescope incorporates the most cutting-edge tech to aid astronomers in learning about the earliest visible years of the universe. With the combination of the HST and JWST, astronomers can see the early universe through multiple wavelengths, ranging from ultraviolet to infrared. The JWST is the key to learning about the universe's birth and many of the theories in the scientific community.